So let's get started with some fundamentals of statistics for machine learning and data science. The definition of statistics is the practice of science of collecting and analyzing data in large quantities, especially for the purpose of inferring proportions in a whole from this in representative samples. Now, what are the elements of this definition? The elements of this definition is that it's a practice or science of collecting and analyzing data in large quantities. Now, as we know that in data science and machine learning, most of your work is going to be involving data. Some part of your work, which is of a much lesser percentage of your work, is going to be around creating predictive models or machine learning models, etc. So large part of your machine learning projects or data science projects are going to be involving analyzing data. So in some of the other webinars, we have explored the various techniques and tools and techniques of exploratory data analysis and statistical techniques, using statistical techniques and creating insights from the data is part of the exploratory data analysis process. It is also part of my exploratory data analysis process, which is directly related to the predictive modeling process as well. I mean, not only the pre-modeling process steps, but also part of the modeling process steps, right? And then when we talk about the application of statistical methods, normally these are used on data which are in large quantities, because in small quantities of data sometimes, or many times we can infer the data by visually inspecting them, but for large amount of data you need to understand various measurements of the data, various insights of the data, and statistical methods are applied on such large amounts of data, right? And the other purpose of using statistical method is that a lot of times experiments cannot be conducted on large populations of data, and we need to work with smaller samples of data, right? Let's say, for instance, there's a popular example that you got a consignment of products, or let's say consignment of medicines, right? You are a medicine distributor and you got a consignment from the manufacturer of the medicine. Now, as a distributor, you also have your responsibility on quality control. So when doing the conducting the quality control, would you really open and test each ampule or each tablet from the consignment that you have received and test them? No, then you are actually destroying the entire population. What is going to be left for you to sell, right? So in these cases, you have a constraint that you cannot work with the entire population. The testing cannot be done on the entire population. You have to work with samples and random samples. And when you make this kind of tests, you take random samples and you carry out your statistical experiments. Now, in those cases, the goal of the sampling and the experimentation on the sampling, or applying statistical methods of the sampling, is inferring proportion from representative samples about the whole population, right? So that is another method or another purpose of using statistical methods. So in summary, you can say that statistics is the art of making numerical conjectures or numerical inferences about your data, about puzzling questions on your data. Some of the questions that we can frame, which can be solved using your data by application of statistical techniques, are like very interesting ones. What are the effects of certain variables over others? Example, effects of a medicine on heart patients. So let's say, for instance, you have bunch of heart patients and you want to understand the effects of various treatments on these heart patients. Now, there are multiple different medicines that are applied on these heart patients. There are certain therapeutic techniques that are applied on the heart patients, and then you observe results on the population, and you try to find out using statistical methods as to which of the variables or the effects of the variables, that is certain medicines, certain therapeutic techniques, on the result on the heart patient. So there are statistical methods that are used to solve this puzzle. What should be the price of a lottery ticket for the lottery company to make a profit? Now this is a extremely important question. So if you are the owner of a casino, or if you are if you are the owner of a lottery house, then you definitely have to make a profit. I mean, that's a business, right? Now in lottery or casino, it is said the house always wins. Now you can never win more than the lottery company or the casino company, right? Because the pricing of the tickets, so pricing of the puzzle is kept in such a way that the amount of money that the company gives out is always less than the amount of money that the company is collecting in the form of ticket prices, right? So what should be the, I mean, using statistical method, you find out this casino companies or lottery houses find out what should be the ticket for ticket price for the company to make a profit. Or for that matter, if you are the buyer of a lottery ticket, or if you are playing the games in a casino, you want to find out, okay, how many times or how many lottery tickets do I have to buy to have a reasonable chance of winning an amount which is more than what I am spending, which never happens, of course. If you make a profit, that is by chance, and if you play a sufficient number of times, your profits and loss will actually even out, and you will eventually make a loss, net loss, over a number of times you are playing on an average. Okay, so these are questions that using statistical methods that you can solve, right? Now there are some different branches of statistics. Some of the branches that we normally use in machine learning data science areas are descriptive statistics, probability theories, inferential statistics, and another thing related to inferential statistics is that tests of significance. Right, these are some of these areas that I have mentioned in statistics. Descriptive statistics is the technique of summarizing and representing data. Metrics such as average, median, standard deviation, root mean square, histograms, etc. are part of descriptive statistics, and these are fairly commonly used when you are dealing with data science and machine learning and your machine learning data science projects. Right, very commonly you need to find out average of numerical features or standard deviation of numerical features. So you need to perform operations like scaling or normalization or standardization on your data, and standard deviation and average, etc. This kind of metric are commonly used in those kind of techniques, right? You need to understand the population pattern of certain features, and you use that by using distribution, population distribution, and using histograms. You visually represent the distribution, and we'll see how we do that both in terms of theory as well as some couple of examples in Python. Right, probability theories are another important branch of statistics, which are normally fairly commonly used. If you have gone through classification techniques, some of the classification techniques, one of the things about classification techniques is that quite a few of the algorithms, classification algorithms, machine learning classification algorithms, output probabilities instead of output classes. Some of the algorithms output classes, and some of the some of the algorithms in classification techniques output I mean the class probabilities rather than the class labels, right? So algorithms such as naive Bayes, if you have gone through naive Bayes classification algorithm, or for that matter logistic regression classification technique, etc. These use probability techniques pretty abundantly. Especially naive Bayes is completely completely based on probability theories to find out the probability of the class level outcomes, right? Then you come to inferential statistics, generalizations or inferences that can be made from samples. So the example that I have given, that if you are in quality control and you are to make an inference about the quality of the population, you can only, I mean, most of the times you can only do that in the physical realm by taking a sample. I mean, in digital realm, you can make testings on the entire population, but in physical realm, you have to rely on sampling, right? So inferential statistics and tests of significance are some of the techniques that are used for making inferences from samples about the entire population, and we will see some brief examples as to how to do that. Now, before we come to statistical method, we have to have a fair idea about the types of data that we normally deal with, right? So when you expect, when you are working on a data science machine learning project, you receive data from your functional systems, and your company is expecting you to create machine learning models, either regression models or classification models, etc. And there are other different types of models as well, on using the data that you receive from your company, right? Now, this data come in different shapes and forms, right? And these are some of the classification that we have, or types of data that we normally encounter. Nominal data are more or less names or labels. So let's say, for instance, in your data set, you have an address, or if you have a country name, or if you have a state name or city name, right? Or the persons, I mean, if there are transactions about persons, then you may have the persons names. So those are nominal data. I mean, they don't have any numerical significance or numerical degree or variance, etc., etc. So they are textual data, they are nominal data. Now then you have ordinal data. Now ordinal data are also textual data. So let's say, for instance, but they have a perceivable degree of measurement, right? Now what is that? You say something is good, average, or say let's say average, good, very good, excellent. Now these are labels, but these have a perceived degree of measurement. They are not just like any city names like Bangalore, Chennai, or Noida or Delhi, etc., etc. So they are not mere labels, but they have a perceived difference or perceived degree of measurement. Say, for instance, CGPA rating of students in a classroom, right? They can be A plus A, B plus B, C. So there is a perceived degree of measurement. Now if you can convert this A plus A, B, C, etc. into 5, 4, 3, 2, 1, that has a numerical significance to the machine learning model, and this kind of values, numerical values transformed from the ordinal values, can be used for your machine learning modeling, okay, normally. Then you have the interval data. Interval data are those data like say, for instance, temperature. Now the characteristic of the interval data, I mean, they are like normal numeric data, but there is no absolute zero for interval data. Now one good example is the temperature. Now is there a absolute zero temperature? I mean, you have 0 degree temperature and plus 20 degree temperature or minus 50 degree temperature, but is there something like absolute zero temperature or null temperature? There is nothing like that, right? So interval data have this degree of or measurement, right? There is a certain degree of difference between 40 degrees and 41 degrees, but there is no absolute zero. Okay, 0 degree is actually not a absolute zero. There is still temperature. It is still temperature, right? So interval data are those data where you have the degree or the level based relationships. You have differences between two values in that based on a particular unit, and you use units. but there is no absolute zero. And the last one is the most commonly used one. I mean, they are our normal numeric values. Is the ratio variable, where you also have a absolute zero. So let's say distance is 0 kilometer. That is actually, there is no distance, right? You are actually talking about a absolute zero here. Okay, so these are the ratio variables. So let's say his income is 0 rupees, right, or $0. So this person doesn't make any income, so there is an absolute zero here. But in case of temperature, there is no absolute zero, right? Hope this is clear. All right, so these are the types of variables that we have, and we have to understand as to, and depending on the type of data that you have, you have to deal with this data. There are different ways of dealing with different types of data in data science and machine learning models. Okay, now there are other types of other classifications of data. One is discrete data, one is continuous data. Now discrete data are numeric variables that have fixed intervals. So let's say, for instance, 5%. You can't have 5.5%, right? I mean, unless you are terming a small child, as a 0.5%, right? I mean, but that's not correct. I mean, that we jokingly say that, but then that's not correct. So you can never have 3.5%, right? Okay, or you cannot have 3 or 4.2 cars, right? Car can be 1 or 2 or 3 or 4, right? A person can be 1 or 2 or 3. So these are discrete data. However, there is also continuous variable. So let's say, for instance, distance can be 5.423 kilometers, or my income is 12,561 rupees 54 paise, right? So these are continuous variables. Now the funny thing about continuous variables is that between any two subsequent or perceivably subsequent or even not non-subsequent continuous numbers, there can be an infinite number of continuous variables. So what does it mean? What I'm saying is that we have two numbers, 5.1 and 5.2, and what I'm saying is that there can be infinite number of numbers, continuous numeric numbers between 5.1 and 5.2. Why is that so? If you just calculate, keep on churning numbers like 5.125, etc., and then 5.1321, etc. That way, when you extend the number of decimal places, you have infinite number of continuous numeric numbers between any two given numbers. Okay, so that's the characteristic of continuous, and which is completely different than discrete. So you can't have 3.5 bedrooms. You can either have 3 bedrooms or 4 bedrooms. You can't have 2.3 persons. You can either have 2 persons or 3 persons, right? So these are the different types of data, and depending on these types of data, some of the statistical methods that can be applied on this numeric variables are this. So we can have a mean, we can have a median, we can have mode, standard deviation, variance, and quartiles, and we are going to look into some of these foundational concepts of descriptive statistics. Now mean is and all this statistics, descriptive statistical terms can be applied on your continuous numeric data. Now, would you really find out the mean of number of persons feature or number of bedrooms feature? It is not going to make any sense, right? If you have observations where you have feature values like 4 and 5 and 6 and 8 and 10, and you try to find out the mean of it may turn out to be 6.7 persons, which is not going to be meaningful unless you want to kind of round off and find out an approximate mean. But an accurate mean on discrete numbers are not meaningful. So mean is actually the average of your data population, and normally apply it on continuous variables, right? Mean is essentially the numeric average. Now median value is the middle value. Now middle value, what do you mean by middle value, and what is the difference between median and mean? The middle value is that, let's say you have 100 observations or 100 rows in your data. The median value is the 50th value, or in case of your number of observation is even numbers, then it's the average of the two adjacent middle numbers of that population. So in case of a population where you have 100 values, then the median is going to be the average of 49th or 50th. No, sorry, it's going to be the 50th value of the population, right? So it's the middle value. Now it has a relation with quartiles. Now quartiles depend on the number of values or number of observations that you have in your population, right? So quartiles, we'll come to quartiles in a moment with a different example of box plots also. Before that, we go into standard deviation, and we have some worked out examples. So let's look at this worked out example and have the understanding of these terms. So if you have the student marks, so let's say student 1, student 2, student 3, and so on, and you have science marks, maths marks, etc., and the student has marks in both these variables, right? So these are your observations. The observations belong to each of the students, and the observations contain two fields or two features. One is science marks and the one is maths marks, right? So you can have an average value of science marks and maths marks for each of the students, or you can also have the average of all the marks here, which is the average of all the averages, right? So this is going to give you the overall average. Now if I have 10 occurrences or 10 observations of my data, then what is going to be the median value of that? Okay, now first of all, what is going to happen is that this data is going to be sorted, okay, and then the 5th and 6th values are going to be taken and averaged out to find out the median value, right? If there are 11 values, then it is going to be the value at the 6th place. So as I said that if there are odd number of occurrences, it is going to be the center value in a rank ordered, I mean when the values are ordered in terms of their values from highest to lowest or lowest to highest. Then if it is an odd number of observations, so let's say 11, then it's going to be the middle value, which is going to be the 6th value. In case the number of observations are going to be even, then it's going to be the middle, the mean the average of the middle two values, right? In case the 5th and 6th. Now it's not this 5th and 6th, it is in the rank order basis the occurrences of 5th and 6th. That is median. Now mode is the number or the value that occurs most of the times or most number of times in this population. Okay, so B plus is the mode for this CGPA population, where B plus is the value that occurs most of the time. So this is the mode. All right, so this is the other statistics that you are getting. Now what is standard deviation? Now standard deviation again is a very commonly used statistics. Standard deviation is the disbursement or the average disbursement or deviation of each of the numbers of the entire population of numbers from the middle value or the central point, and the central point in our case is going to be the mean value or the average value of the population. So let's say we are dealing with the same data, but here in this case we are taking the science marks feature. So these are the values that we have got, and we have got the average of 77. Now what standard deviation is going to mean is that what is the average deviation of this population from this middle value, which is 77. Alright, so it is calculated as a root over the sum of squares of averages. So that means this formula, so sigma is normally is a notation that is used for standard deviation. So the formula is that xi minus the summation of all xi's minus mu is the average value, which is 77 squared divided by n root over. So what does that mean? That means that for each of these values 67, 78, 76, what we are going to do is that we'll take 67 and average is 77. So 67 minus 77, that is going to be minus 10 squared, so that is 100, plus 78 minus 77, so that is 1 squared, so that is becomes 101, plus 76 minus 77, that again is 1, so 102, plus 89 minus 77, and so on. Okay, divided by n. What is n? N is the number of observations here, so which is 10. So the value that we have got here, by summing up all the differences between individual values and the average value, the mean value, squared up, divided by 10, that is an averaging it, and root over is going to give you the standard deviation of the population. Okay, so this is how the standard deviation is calculated. So essentially it is to calculate the central tendency, or rather the deviation of or the spread of the data from the mean. Okay, the average spread or average deviation of the data from the mean. In our case, when we apply this formula on this particular data, our standard deviation comes to 10.5. So on an average, each data point, each of these data points on an average are 10.5 numbers away from the mean. So either it can be either negative or positive, right? But this is the average disbursement or deviation or spread. Now there is another important concept about data is distributions. Now distributions is how the data looks like, right? Now in our EDA session, I mean, if you have attended our exploratory data analysis session, you would have seen we have dealt with the distribution, we have plotted distributions, etc. Now what does distribution mean? Distribution is part of univariate analysis, univariate data analysis. What it means is that we count the number of occurrences for each range of values from your population. Right now, some of you may have heard about bell curve from performance management or performance appraisal point of view in your organizations, right? What does it mean? That means that if you just break down that example of performance evaluation, there are performance bands in an organization which are within the scale of 1 to 5. Now 1 means if somebody gets 1, that means that the person hasn't performed good at all. I mean, it's falling way below the expected levels of performance. 2 is still bad. 3 means met expectation. 4 is very good, met expectation and gone beyond, and 5 is outstanding. So these are the performance bands the organization uses. Now company says, the HR policy says that okay, we are going to fit the employees in the bell curve. Now what does that mean? That means that the maximum population, maximum number of employees are going to get the average or met expectations rating of 3. Okay, so that is why and fewer number of people are going to get 2, very few number of people are going to get 1, few number of people are going to get rating 4, and very few numbers are going to get rating 5. Okay, now if we just count the number of employees getting 1 rating, probably it is, let's say, 100. People getting rating 2 are probably to the tune of 300. People getting rating 2 is 300. People getting rating 3 are probably about 1200. Okay, forget about this scale. I'm just taking the number from our example. Number 4 is again 300 to 350, which is about similar to the number of people who have got rating 2 also, and about 70, 80 or 100 people have got rating 5. Now if you plot the distribution of how many people got a rating of 1, how many people got rating of 2, how many people rating 3, 4 and 5, it is going to look like a bell, and that is why it is called a bell curve, right? It is probably the most commonly known example of the bell curve, but bell curve is a statistical term. It is when your data shows this characteristic of bell curve, that means for a particular range of values, that the maximum population range, maximum population lies within a particular range of values, and the dispersion or the distribution looks like a bell. It's called a normal distribution or a Gaussian distribution or a Laplace Gauss distribution. So there are different names that are used here, but it essentially is the same thing. It's a normal distribution. Now normal distribution, why this is important? Of course, from the employee performance appraisal point of view, we have explained why this is important. It's HR's policy of fitting maximum number of people in band 3, etc., etc. But mind you, it's a very naturally occurring phenomena in the world of data, right? So let's say, for instance, in your quality control of products, right? So let's say you are working for a cold drinks, soft drinks company, and you are in the quality control department, and you are given the task of measuring the lead content in the soft drink. Okay, so let's say the soft drink level that is allowed is about say 1 microgram per liter, right? I don't know what it is, but let's say 1 microgram per liter. That should be the permissible lead content. Now if you take a sample, you get a consignment from the manufacturing plant containing, let's say, 1 million bottles, and you take up for quality control purposes, you take you get into different boxes and different containers containing those 1 million bottles, and you take samples from different places, right? Okay, so one box may contain a similar characteristic, but you for randomness, for carrying out a random experiment, you take samples from different places of that consignment, and you measure out of a total population of 1 million bottles of soft drinks that your plant has just delivered. The manufacturing plant has just delivered. You pick up a sample size of 100, okay, 100 bottles, and from random places. And then you try to find out the lead content in each of them, and this is what you find out. It is very likely that you will have a small amount of bottles which will have a significantly lower lead content than the permissible level, and you will have a significantly large population of bottles, say about 70, 60, 80, that conform to the range of permissible levels of lead content, and a very small minuscule percentage of bottles that will actually have lead content way above the permissible levels or permissible limits, right? So this is a very naturally occurring phenomena in the world of data, in the world of quality control, etc., etc. Say for instance, income levels of people in a state. you will have a very few people who are going to be extremely poor, and you are going to have very few people who are going to be extremely rich, and everybody in between are in the large population, which is the top of the bell, right? So you see that you can relate it to real life cases. This Gaussian distribution or normal distribution is not only limited to employee appraisal, but it is a naturally occurring phenomena in the world of data. So let's say people buying pattern in a e-commerce site. So let's say I mean, if you calculate, I mean, if you take a population of 10,000 people who have purchased something on Amazon, and Amazon creates a distribution curve. I mean, this is also a distribution chart, and find out what is the distribution of people who have, based on their purchase amounts, okay, in the last 6 months. You will most definitely find a range of purchase amounts which are going to be around a middle value, right? A central value or an average value. Okay, very few people are going to be in the zone where they have spent very little, and very few people are going to be in the zone where they have spent very highly. Okay, so all this data conform to a normal distribution or Gaussian distribution or a Laplace distribution. So understanding this normal distribution and its significance in relation to our dealing with data is very, very important. Okay, and in Python you can draw a distribution chart using a histogram feature, either from Seaborn library or from Matplotlib library. You can draw a histogram like this or like this to understand the distribution of data. So let's say, for instance, Usain Bolt is taking practice sprints, and he's a Olympic champion runner or sprinter of is a 100-meter Olympic champion. Now he's collecting data about his practices, and he's trying to find out how many times how much do I clock on an average basis. So if you if he takes this, I mean, plots that data in histograms, he is clocking between the times of 10.1 to 10.3, etc. This range, the maximum number of times, and there is a small number of times he is clocking very, very low, so he's running super fast, or a small number of times he is very slow, is clocking about 10.5, etc. Okay, so this is also called a frequency distribution chart. However, although normal distributions are very important, and understanding of normal distribution, understanding the distribution of your data in your input files is very, very important. And there are algorithms which will ask you that I want normally distributed data. Say, for instance, your naive Bayes classification algorithm. There is a variant of naive Bayes classification algorithm which specifically assume that the data that you are feeding to it are from a Gaussian distribution, right? Say, for instance, linear regression also. There are times that it assumes that data that you are feeding it are normally distributed. Okay, or for instance, the residuals that linear regression is producing, it is normally distributed, and there are tests to find out whether the residuals are actually normally distributed, right? So that is why the normal distribution and basically understanding distribution is very, very important. Now there is another way of finding distributions and dealing with distribution is in this with the study of the quartiles, right? Now you have minimum values, you have maximum values, you have median values. So minimum values and maximum values are no-brainers. You know what is minimum value or maximum value of a data population. But you have also heard about medians. Median is a middle value, right? So it's not the average value, it's the middle value. If you have x number of population, it's the middle x in a rank order. I mean, the values are when the population is organized in terms of ascending order or descending order, it's the middle value, right? It's not what you see visually. is the in sorted order, it is the physically middle value of that population, right? So but it is also sometimes important or interesting to understand the overall distribution of the data, not only understanding the minimum value, maximum value, or the median value and the mean value, but it is also good to understand sometimes as to overall between the mean and the maximum values, and even between mean value and the or minimum value and the median value, and the median value and the maximum value, how are the data distributed. Okay, so the box plot is the solution for that. If you want to understand as to and this is the value ranges. I mean, this is not the number of observation. This y-axis, or this in this case the vertical axis is the values distribution or the value scale, and in this particular case, 0 is probably, I mean 0 or something very close to 0 is the minimum value, something very close to 500 is the maximum value, something which is about 250 is the median value, about 380 or 70 is the 75th quartile value, about 120 or 40 is the 25th quartile value. Now this particular line in a box plot, this is a box plot representation, which is another way apart from the frequency distribution chart. The frequency distribution chart is what we saw in the previous slide. So these are frequency distribution chart, a frequency distribution graph, and the box plot is another way of plotting the distribution. So here you see that how many, these are 25% of my observations. So if there are 100 observations or 100 values in your distribution or in your population, then this segment here or this section here represent 25 observations, okay, from the bottom, and these are sorted in the upwards in the ascending order, right? So from the minimum value, from the lowest value, the first 25 are between 0 and about 110 or 120 here. So that means it is interpreted as about 25, the first quartile or the first 25 values in my population are between 0 to 120. The next 25 observation in my population are between 120 and 350. So if you want to interpret this kind of insights or get in this kind of insights about the distribution of your population, then you have to use a box plot, and the box plot is going to give you the 0th percentile, the 25th percentile, the 50th percentile, the 75th percentile, and the 100th percentile, which is the maximum value, and the 50th percentile value is your median value, right? Each of these are 25% segments in the rank order basis, in the value order basis. Okay, so that is box plot, and there is also another term called interquartile range. This part is the interquartile range. So the distribution between 25th percentile and the 75th percentile is also called the interquartile range. So if I ask you what is the interquartile range for this particular population, you have to say that the interquartile range for this particular population is between 120 to 380. Okay. Now there is another very interesting thing about normal distribution of data, which is called the normal approximation. Now these rules apply for most of the normally distributed data. This rule says, the normal approximation of data, these rules say that 60% or 68% of the data will lie between standard deviation of -1 to 1. 95% of the data will lie between standard deviation -2 to 2 plus 2, and 99.7% of the data will lie between standard deviation of -3 to plus 3. Now what is standard deviation -1 and 1 and -2 and 2, etc.? Let's go back to the standard deviation calculation that we have conducted here. So using this standard deviation formula, we have found out that our standard deviation is, for this particular population, is 10.5. Now this value is inferred as one standard deviation. It is not 10.5 standard deviation, it is one standard deviation. So for this population, one standard deviation is 10.5. Now with that in mind, what we say is that we bring up the notion of or the concept of standard units. So for that population, after you calculate the standard deviation value, so let's say it is that population of student marks, and each unit of standard deviation is 10.5. The one standard unit for that population is 10.5. Now what we are saying is that 68, according to normal approximation of data, 68 or approximately 68% of data will lie between 1 -1 to 1 standard deviation units or standard units in your bell curve or your normal distribution curve. Similarly, 95% of your data will be lying between -2 to +2. Okay, and this is because of the shape of the bell curve or the shape of the normal distribution curve. Okay, so if you see that as you go to the left hand side or the right hand side, the graph tapers off. So that means there are very few few amounts of data in your entire population that will lie beyond -3, -2 or -3 and +2 and +3 standard deviation, and these are results of a lot of empirical evidences, a lot of empirical studies, and finally scientists have come up, or statisticians have come up with this kind of figures, and that if your data is normally distributed, these are the kind of approximation that you can expect to observe, right? So this is a normal approximation of data, and there is a lot of inferential statistics that are based on this normal approximation of data rules. Okay, you will see later on. Today we will touch upon some things briefly, but when you go deeper into statistics, you will learn some of this. Now we touch upon briefly into probability theories. So probability theories are basically for chance events. Okay, now what are chance events? Chance events are say for instance roll of a dice. Okay, so you don't know when you roll a dice, right? Say you are playing Ludo. Okay, a very popular game among in India. When you are playing Ludo or snakes and ladders, then you roll the dice. So when you roll the dice has 6 ends or 6 sides, and on each of the sides you have 1 dot or 2 dots up to 6 dots. So you don't know when you roll the dice as to what is going to be the what is going to come up. Okay, so will you get 1 dot side upwards or 6 dot side upwards? You don't know. Now I want to know what is the probability that I am going to get a 1 dot side or a 2 dot side or a 3 dot side individually. Okay, and of course you can understand intuitively that the chances of, or the probability of you getting a 1 dot is equal to the probability of getting a 6 dot side upwards. Okay, and what is that probability? Of course, what are the total number of possibilities that you have? 6, because it can be any of the 6 possibilities or 6 sides that can come up, right? So the probability is simply 1 by 6, which is 16.7%, right? So if you have 6 possible options, any of this getting the probability of getting any of these sides is going to be 16.7%, which is simply the division between 1 by 6, right? So that is this is how probabilities are calculated, right? The probability of something is denoted by the percentage of time it is expected to happen given the experiment or process that is repeated over and over again, keeping the conditions of the experiment same. Now what does it mean? What it means is that if you roll the dice, let's say 10 times, 6 possibilities. Now in this 10 times, you are going to get the two sides. You are not going to get the sides the equal number of times. Okay, it may be so that the 6 dot side came up 4 times. You may be very, very lucky, and for you, the 6 dot side came up 4 times. Now for a small number of experiments, a small number of occurrences of your chance event, your probability or the actual result may not be equal to the probability that you have calculated, that is 16.7%, because if out of 10 6 dots come up 4 number of times, then it definitely is not complying to the probability that you have come up with, right? You have calculated the probability is 16.7%. So I expect out of 10 occurrences or 10 times I roll the dice, the 6 dot side to come up once or twice maximum, right? But it has come up 4 times. So for a small number of experiments, in your probability calculated value may not be complying to the actual results that you have got. But if you experiment sufficient number of times, so that is what it is saying, that if the process or experiment is repeated over and over again sufficient number of times, then the actual result is going to be similar or very near to the probability that you have calculated in theory. Okay, the notation of indicating probability is by letter P, and the probability value is always used as a value between 0 and 1. So either 0.16 or 0.167 or 16.7%, or is a value between 0.0 to 100. Now there is also the flip side of what is the probability. I mean, we were asking the question that okay, what is the probability of us getting a side with 6 dots? Now if I ask what is the probability of us not getting a side with 6 dots, what is going to be the result? So we calculated the probability of us getting a side with 6 dot is 16.7%. But what is the probability of we getting a side which is not the side of 6 dots? And the answer is 1 minus this. Okay, so the chance of an opposite event happening is calculated as 1 minus the probability of the original outcome. So if the chance of we getting 6 dots is 16.7%, the chance of we not getting 6 dots is 1 minus 16.7%, that is 83.3%. Okay, so basically that is the addition of the probabilities of we getting 1 dot plus 2 dots plus 3 dots plus 4 dots plus 5 dots. Now there is another important concept in probability, which is called the conditional probability. We'll just touch upon the concept. We'll not get into the formulas of how conditional probability is calculated and etc. That's going to take time. We are already over 1 hour. Now what is conditional probability? Let's say take a situation that we have a bag with 5 green balls and 4 red balls to it. Okay, and we want to find out if we draw 2 balls in succession, what is the probability of the second ball being red? Now there can be 2 scenarios. There can be multiple scenarios, but let's talk about these 2 scenarios. Now the first ball is drawn, the color is noted and placed back into the bag. So just note that we have placed it back into the bag. Now then, what is the probability of we picking up a red ball in the second instance? It would have been the same as the probability of picking up a red ball in the first instance as well, because of the replacement. Okay, now if you haven't replaced, which is our second scenario, if you haven't kind of the second scenario, if you haven't replaced, then the probability would be different. But if you have replaced the ball which you have drawn in the first occurrence, then the probability of picking up a red ball in the second instance is going to remain same. And what is that probability? The probability is 5 balls green balls plus 4 red balls, 9 balls in total, and 4 red balls in total. So 4 divided by 9 is going to be the probability of picking up a red ball. So 44%. Right now, then change the scenario a little bit and say that what is the probability of the second ball being red given the first ball is green. Now then also assume, which is not written here, but also assume that it is green and you haven't replaced it, right? Now this is a situation of conditional probability. Our question now is, what is the probability of the second ball being red given the first ball being green? Okay, now this is the case of a conditional probability. So what is the result? The result is, now after a green ball is picked up and it hasn't been replaced into the bag, we have 4 green balls and 4 red balls in our bag. So that means the probability of the second ball being red is going to be 4/8, which is going to be 50%. So this is a case of a conditional probability. So there are various methods of there is a formula for calculating conditional probability, and we can take a scenario and calculate it, etc., etc. Then it also leads to a very famous theorem called binomial theorem for probability, and then those are going to take time. Now there is also another concept we will touch upon briefly, which is expected value, which is a chance process. Okay, so every chance process, and what are the chance process? So rolling of a dice is a chance process. Okay, we can't predict the outcome. We cannot expect an outcome. We know what is the probability of finding a particular outcome, but it is a chance process, right? Picking of the ball from the bag is a chance process. We do not know the outcome. The outcome is purely by chance, but we can calculate a probability of the chance to materialize, a particular expected outcome to materialize. There is a probability. Now if it says each of the chance processes produce a quantifiable outcome. A series of chance processes produce a cumulative outcome, which is called the expected value. Now we take the example of the lottery ticket we were talking about before. Okay, in the lottery ticket example, let's assume that there are 1,000 tickets that the company is issuing, the lottery company is issuing. Each lottery ticket is priced at $10. The winner gets $1,000, and if you buy 10 tickets, how much can you expect to win? Okay, my question is, if I buy 10 tickets, how much can I expect to win? Now the solution is, I mean, this is a very simple trivial example. You can calculate it in your mind, but in more complex scenarios where more variables are involved, that there is a expected value calculation that needs to be applied. Okay, so a ticket is a chance event in this case to being a winner. Each ticket being one out of the total 1,000 will have a possibility of winning 1. Why? Because the winner gets 10,000 and winner gets 1,000 and 1,000 tickets are issued, and each of the tickets get a possibility of winning $1. Okay, simple calculation. And if you buy 10 tickets, you expect to win $10. So this is based on based on probability of this chance outcome. What is the expected cumulative value from this process? If you run the chance event 10 times, so buying the lottery ticket is the chance event in this case, and if you carry out this experiment 10 times, what is the expected value, total cumulative value that you expect to have, right? And the expected value calculation is given here. Expected value is the number of events. So in this case, number of events was 10. An average possible value on each event is $1, and that was our result. Okay, we will stop here and we will get into Python examples a little bit. So let's go through a few simple examples of application of statistical commands or statistical methods in our data. So what we do is we import a file called car price assignment, and this contains details about car price, car sales transactions. So what it does is that it has a number of features which are about individual cars. Say for instance, car name, Alfa Romeo, aspiration, standard aspiration, door number 2 or 4, drive wheel, rear wheel drive or 4-wheel drive or front wheel drive, etc., engine allocation, horsepower, fuel system, compression ratio, etc., etc., and the car price as well. Now there are a lot of statistical information that we can get from this data. Some of it we have covered in the exploratory data analysis session also, but we'll quickly cover some of the foundational, basic ones. Now there is this pandas function called describe, which is going to give you the basic descriptive statistical information about your data. Okay, so let's say for instance car length. The number of counts is 205. The mean value of car length is 174, let's say inches or centimeters, I don't know. Standard deviation of this particular feature is 12.33. The minimum value is 141. 25th quartile is 166. 58th quartile 173. 75th is 183, and max is 208. So these have given you all the statistical information that we have just learned. So that is coming from describe. Describe picks up all your numeric fields, continuous numeric variables, or even discrete variables it'll pick up, and for any numeric field it is going to give you this statistical information, right? But there are other features that you can use, other functions that you can use. So car sales dot horsepower is referring to the horsepower feature here, and you want to mean value, find out the mean value for this particular feature. So this is 48. So if you look at this one, you will get the mean value as 48, right? But you can, if you want to extract this feature separately, you can do that. You can also find out the mean value. So this is the minimum value, this is the mean value 104, max value or the median value is also possible. So that is 95, and you can see this is the 50th quartile. So your median value is actually the 50th quartile value for that particular feature. Okay, the mode value. Okay, so what we did is that we haven't taken the mode for the numeric features, but we have taken the mode for this car name field. So basically what we said for mode is that it is the value or values that occur the maximum number of times. Okay, so Peugeot 504, Toyota Corolla, and Toyota Corona, I mean that's a misspelling in the data, in your data. This occurred the maximum number of times, and probably equal number of times, and that is why these three values are being brought up as the mode for car name in the car sales data. Okay, right, then we check out a few more. So we have seen the normal distribution, distribution plots, and we have seen the examples of Gaussian distribution or normal distribution. So essentially any distribution of feature value distribution of any feature can be done, can be visualized using the dist plot, and there is an equivalent in matplotlib also, but we are using the seaborn dist plot. And this is we said it's part of a univariate analysis, and by which what we mean is that it's analysis on a single field and not interrelations between multiple fields, right? So that is why univariate analysis. And what we do is that we pass on the price field in dist plot, and this is the distribution. So what it means, this distribution means is that, and we see that this is not normally distributed. What it means is that you have maximum number of cars in the price range of 10,000 to 15,000, 16,000, etc., and then it tapers down as the value of the price of the car increases. Okay, and in the extreme range it's a very minuscule number. And the same thing we are doing as we saw an example of box plot, and interpreted our box plot in terms of the minimum value, the maximum value, and the quartiles, 25th quartile value, median value, etc. So this is the box plot for interpreting the car price distribution in terms of quartiles, right? And you can do that by SNS box plot feature, and then pass on the price feature into the SNS box plot method, right? Then if we, so these are so price is a continuous numeric field, but if you want to check out the distribution of categorical values, let's say for instance aspiration, there are two possible values, standard aspiration and turbo aspiration. So what you want to do is that in my total distribution, I want to find out the number of times the standard distribution the standard aspiration occurs, and vis-a-vis the number of times the turbo aspiration occurs. Similarly, for fuel type, there are two types of fuels, gas and diesel, and I want to have a distribution comparison between the number of occurrences of gas and diesel. Similarly, for car types, there are different types of cars, sedan, hatchback, wagon, hardtop, and convertible. Okay, so sorry, this texts are very small, so I was struggling to read it. And you can get this kind of so the difference between the previous one and this one is that this is the univariate analysis or distribution for categorical variables, whereas this one is a continuous numeric variable. Okay, distribution of a continuous numeric variables, right? So for continuous numeric variables you have ranges, whilst for categorical variables you have fixed values, right? So that is a difference. Okay, and what we have done is that we have plotted a matplotlib bar plot. So plot data dot plot, and the kind of plot we are passing as bar, right? And what is the data? The data is aspiration is our field within the car sales data frame, and the value counts is going to give individual value counts for every possible value in this field. So what are the two possible values in the aspiration field? The standard and turbo. Okay, so value counts is going to return standard followed by the associated number of times standard occurs, and turbo and the associated number of times turbo occurs in the data set. Okay, and we plot we use a matplotlib bar plot to plot this bar plot. Okay, so and we do the same thing for fuel type as well as car types, right? So these are some of the examples, simple examples of what we have just learned in our session, the statistics session. Thank you for attending the fundamentals of statistics for machine learning and data science. Thank you.